Today's lecture is going to be on ocean modeling. So let me share my PPT now. Let me see if I can share it. So are you able to see my screen now?
No.
No, until not.
Okay. What about now?
Yes, it's visible now.
Okay. Okay, so this lecture is on ocean general circulation modeling. Now, ocean is a very important part of the climate system. Oceans have a very major to play in terms of controlling our weather and also the long-term climate of. In fact, this is mainly due to the reason that the specific heat capacity of ocean is very high because it's all water, and water, as you may know, has one of the highest specific heats. It takes a long time for the oceans to heat, and it's a long time for the oceans to cool. So if you had listened to some lectures on climate change, you might have also learned that the oceans also have been warming. In fact, of the global warming that is happening, a good part of the heat energy is stored by the oceans. So owing to these reasons in particular, the ocean has a very important role to play in our climate system. Now, the other thing is that the ocean can also initiate and amplify climate signals. So you might have seen that in the recent last week, in fact, Bangalore received a lot of rain, and these rain came from the weather system that formed in the Bay of Bengal and in the Arabian Sea. The sea surface temperature is very important for increasing rainfall because it fosters large amount of cloud formation. So when we look at long-term climate events like El Nino, and El Nino has a major impact worldwide on the weather and climate. Indian monsoon is very severely affected by El Nino. So owing to all these reasons, oceans have a very important role to play in our present climate. Now, the other thing is, which comes in terms of the physics of the climate system, is that the ocean has a role to play in transporting the excess heat that is received in the tropical region to higher latitudes. Wow. Yes. So if you are not speaking, please keep your mic muted. If you have any questions to ask, you can switch on the mic and ask questions. I don't mind somebody interrupting my talk to ask a question. Okay. So what is required? We need to understand the ocean, and in order to understand the ocean, we have to measure the oceans. Now, measuring the ocean is not easy because one reason is that the oceans are very vast. So when to measure and where to measure is an important issue. Also, it is very expensive to do measurements in the ocean. We need either ships or we need either satellites, and now we have automatic robotic instrumentation to measure the ocean. But all these are very, very expensive. Now, even when we can afford it, covering large areas of the ocean is very difficult because, as I mentioned, the ocean is very vast. And so, whatever observing system that we are setting up is too insufficient to cover all the spatial scale that we want to look at. Now, what is spatial scales? Spatial scale is related to the number of observations or the interval of observations that is required to sample a system completely. Now, I'll come to this in a little later. Now, so what happens is that ocean is an undersampled system. It's a natural fluid system, of course, but it is undersampled because we don't have the capability to do measurements at all the time and spatial scales that we wish to. So that is where the ocean modeling comes to our rescue to some extent. Because if we have a global model, we can run it the way we wish. We can increase the resolution. We can sample it every centimeter if you wish, or every second if you wish. Of course, you need to have powerful computers and storage, of course. However, it gives you a facility to recreate the ocean in a computer in terms of data. So that is why the ocean models are useful. It is useful to simulate the oceans in order to understand the basic processes, their interconnectivity and variability. So there are a lot of features in the oceans. So if we are able to simulate them, we would be able to get a proper description of those features. Okay. Now, when there is a feature, we would like to know why it is there and what mechanism drives or makes those features to form, and how it is connected to other features and how it varies from in space or in time. So all these things can be done using an ocean model. Now, the prospects are impressive, yet there are many challenges. So first of all, ocean is a turbulent fluid. So ocean is always in motion. There are ocean waves, there are ocean currents, and various things happening like convection, and there is subduction and various things happening. So ocean is turbulence, and turbulence, as you know, is still not a very fully understood phenomenon. The other contribution comes from the rotation. The oceans are sitting on the surface of the earth, and earth is always on rotation. It is rotating all the time. So because it is rotating, the usual equations that we use for example, in fluid mechanics requires some additional terms to be in the system so that the rotation can be properly described. Additional complication comes from the factors which force the ocean. The ocean circulation is driven by winds. It is winds which drives the ocean currents. In addition, there is heat fluxes. The heat flux mainly comes from the solar radiation. And then there are freshwater fluxes. It comes from either snowfall or rainfall. Whenever there is rainfall, there's a net gain of freshwater by the oceans. And whenever there is evaporation, there is a loss of freshwater by the ocean. So these gain and loss of properties would change the ocean characteristics. So it is worthwhile to be reminded that the ocean density is a function of temperature, salinity, and the depth at which it is sitting, the pressure. So whenever there is heating happening, the density would decrease. And whenever there is loss of heat, when the ocean is cools, its density will increase. And so if this phenomena has a spatial structure, that means if there is an increase in density in one place compared to a decrease in density in another place or lowering of density, that would set up a density gradient. And this density gradient can lead to change in sea surface height. And when the sea surface height is changing, water would flow from the place where it is high to the place where it is low. So all these forcing functions have its own corresponding responses. A similar feature would also happen with freshwater fluxes. If there is a gain of freshwater, then it will dilute the seawater locally, and it will decrease the salinity locally, and it would also decrease the density locally. If there is evaporation, on the other hand, the opposite would happen. So all these processes have important implications to ocean circulation, its temperature, and salinity. Now, all these processes are written in terms of equations, right? There are these Navier-Stokes equations which can be written, and these equations represent conservation of momentum, conservation of energy, and conservation of mass. So if we can solve this equation based on the forcing that is applied, it is possible to obtain the fields of that are required to describe the ocean. Well, now there are some things which we do not understand well and which cannot be written well properly using the equations. And these are related to, for example, internal mixing that is happening at very small scales, and the friction happening with the boundaries. So there are these additional physical processes which are not very well understood. Yeah. So now to summarize what I said just now, the ocean is sitting on a rotating Earth, so we call it a rotating ocean, and then it is stratified. What's meant by stratification? Stratification depends on density. If density increases as a function of depth in the vertical, we say that it is stratified. Okay. Depending on the gradient of density with the depth, the gradient of density with the depth gives you a measure of the stratification. If the gradients are very high, it is strongly stratified. If the density variation is very less, it is weakly stratified. Why is it relevant? It is relevant for mixing, because if the state of stratification can be perturbed, it can lead to mixing. So consider a simple situation where you have uniform density. Okay, so assume that you have a depth of about 100 meters and density is uniform, which means it is well mixed. Now assume a situation where you are altering the surface density. Suppose evaporation is taking place. When evaporation is taking place, the ocean surface cools, and the ocean surface cools, then its density would increase. So what do we have? We have profile which was uniform initially. Now we have increased density of the surface water a little bit. So that's an unstable situation. So that parcel would sink. And in this particular situation, it can sink all the way to the bottom of the ocean. So therefore, stratification is very important. So in one phrase, it is a turbulent fluid driven by mechanical energy, which is mostly winds, and then buoyancy forcing. And what makes it very important is this high heat capacity, which provides provides the ocean with a long memory to remember what has happened. There are different types of models. This is also because the scales and phenomena in the ocean are very different. Now, the first one that I have listed is tidal models. Now, tide is one of the most simpler phenomena that has been understood, because you might know that the tides are mostly governed by the attraction of the sun and moon, and these are very regular forces, and it applies on the entire body of water. So the consequence of tides are felt highest very near the coast. So whenever you have high tide, the sea level goes up near the coast, and when you have low tide, it goes down. So this tidal equations are easy to solve, and however you require the bottom topography and geometry of the basin, you are concerned with so on. So it is not necessary to solve the complete set of equations for the global ocean often in order to obtain an idea of tidal levels at a region near the coast. Then there are ocean surface waves, and there are models which are exclusively designed for simulating ocean surface waves. So this again is a problem where the ocean surface waves are generated by winds. So one could write an appropriate equation for the waves and then solve them for the ocean height, ocean wave height, and their period, and so on. Now, another very important phenomena in the ocean which is very highly relevant to ocean atmosphere interaction, cloud formation, monsoons, cyclones, depressions, and so on, is mixed layer process. So mixed layer is the uppermost layer of the ocean, which we generally consider to be well mixed. And this mixing happens because of winds. So often the temperature and salinity are uniform within this mixed layer. So the degree up to which the ocean can cool, or in other words, the degree up to which the ocean can provide heat energy to an atmospheric disturbance depends on the mixed layer temperature and mixed layer depth. So owing to this reason, the mixed layer physics has found a lot of relevance in the study of weather and climate. So we have simple models which are very good to simulate the time evolution of mixed layer. Means how does the depth of the mixed layer change? How does its temperature change? How does its salinity change? And so on. This is a class of models called mixed layer models. Now, when we come to climate or to large-scale circulation, we have the so-called ocean general circulation models. That's what we are going to deal with today. And these models can be either global, covering all the oceans like Atlantic, Pacific, Indian, the Arctic, and the Southern Ocean, or it can be regional. For example, we mostly deal with Indian Ocean model, which is models which are meant only for the Indian Ocean, and such models are called regional models. So that's what I'm going to focus in this talk. Now, even the ocean general circulation models can be classified into some different sets. So this is depending on various approximations in the physics and the design of the model that we are considering. So when we look at physics, we can look at hydrodynamic models. We can look at thermodynamic models, and we combine both hydro and thermodynamic models. That is what we are going to deal with. The other consideration is about how the surface of the ocean is dealt in these models. Now, why is this important? So for those who have been to the beach or into the sea would see that there are waves at the surface all the time. Now, when we construct a model, it is not often very easy to adapt these surface structure to a model. So often what is done is that these surface undulations are often very small compared to the length of the ocean, and also its impact on other features are considered to be can be neglected. So often it is assumed that we need not consider the surface waves. Instead, we assume that the ocean surface is flat, like a tabletop. Okay. Yet, still, it can support ocean circulation, and the models can reproduce temperature, salinity, and everything. Such an approximation is called rigid models. So rigid models also helps you to run the models much faster because it provides some simplification to the time dependence of the numerical scheme. But with the evolution of computers, with the computers becoming very fast, now it is possible to have a free surface. And this free surface, please remember that this free surface is not meant to reproduce the surface waves, but undulations of the ocean surface owing to large-scale circulation can be reproduced, can be solved in models. Now, in the present scenario, the models are basically classified in terms of how the vertical grid is designed. This is very important because there are three issues to be considered there. One of them is convenience, and the second issue is the ocean topography, and the third issue is the structure of water that is held in the ocean. So let me give you a feel of each of these things. So if you want to look at the convenience of designing a vertical grid, we would go with a fixed level model. For example, take a depth of 1,000 meters. So we want to find the solution at every 100 meters. So what would we do in a simple situation? We would take this 1,000 meters and divide it into 100 levels, so that we have a solution at every 10 meters. So these levels do not change. It remains same everywhere. For example, in this particular case, we have 10 meters, 20 meters, and so on. I will show you a picture soon. So that is a very simple thing. But in the ocean, that is not really ideal, because the structure of water within the ocean depends on the density. Lighter water sits at the top, and heavier water sits at the bottom. And this is not uniform in space. Okay. For example, take a density of 1,030. Okay. Seawater density is higher than the density of water. Take a density of 1,030, for example. So at some place you might find the 1,030 density is at a depth of about say 500 meters. But if you go further down or further away from that location, that density may be seen, for example, 100 meter below or 100 meter above. So this is because the distribution of water in the vertical is based on density. So there is another class of model which considers this density levels as the criterion for defining the vertical distribution in the models. So such models are called isopical models. The third class of model is sigma coordinate model. This is mostly applied to coastal region. Now, when we come to coastal region, the depth matters. How the depth changes from one place to the other matters. So there is a class of model which has its vertical grid in terms of how the depth is changing. Now, what are the equations? The equations that are solved. Are you able to follow the slides, and is my talk reaching you properly? Audio is okay?
Yes.
Yes, sir.
Sure. Yeah, since it is all online, I can't see you. It is good to have some feedback once in a while. Fine. Right. So here are the equation that is a simplified form, a simplified set of equations that are solved by ocean models. So the first equation is the U momentum equation. The second equation is V momentum equation. The third equation of momentum reduces to hydrostatic equation for the ocean. In fact, there are also non-hydrostatic models. Then we have a continuity equation. Then one equation for temperature and another equation for salinity. And the last equation is equation of state, which gives you density from temperature and salinity. So let's briefly go through this equation once. Let's take the first equation. The first term is del U by del T. U is the zonal component of velocity. And small t is time. X, Y, Z, small x, Y, Z are coordinates in space. So the first term is the time dependence. That is del U by del T. How the value of U changes as a function of time. And that's what we want to find out. So the second set, that is U del U by del X, V del U by del Y, W del by del Z, are the so-called advection terms. So del U by del X is the gradient, that is change of U in space, and how that change is moving from from one place to the other is governed by the advection. The last term on the left is FV, which takes care of the rotation. That's a Coriolis term. F is the so-called Coriolis parameters. On the right-hand side, we have first term as a pressure gradient force, and then three mixing terms, two in the horizontal and one in the vertical. So in an ocean model, what we do is we just retain the first term, that is del U by del T on the left-hand side, and everything else is moved to the right-hand side. So what do we have now? We have del U by del T. That means rate of change of time with U with time. Okay, and so now all terms except the first one has moved to the right. Okay, and now you write a numerical equivalent of it. So what it would give you is U at time t, for example, and then U plus time at a later time divided by the time interval. So now if you keep just say future time on the left hand side and the past time and the time into the right hand side, you have the solution for U numerically, right? So that's a very general description of how you go from this equation to finding the value of this. So if you look at all these equations, U momentum, V momentum, temperature and salinity, they have time dependence. So they are so-called prediction equations or prognostic equations. So they have to be solved by the method which I described just now. The two other equations, that is continuity and hydrostatic, they don't have time dependence. So if you know the value of U, V, W and density, then you can U, V, W and density, then you can calculate those values. So they are called so-called diagnostic equations. So this is in nutshell what an ocean model is. An ocean model is a solution to a set of these equations. So this is the basics for all models, whether it is a regional model, whether it is a global model, whether it is a fixed level model, whether it is a sigma cotangent model, these equations are same. Only how you construct the model would be different. So let's see how you do that. So all this have to be, these equations have to be transformed into a grid because these are numerical solutions. So we need to find the solution at every point that we want to. So we have to define a grid. So this is, for example, a horizontal grid, a top view. I don't want to go into the details of it, but we have various variables like U, V, eta for the surface height and so on. So there are various grid schemes like Arakawa, A grid, B grid and so on, which helps you to construct these grids of different variables in space. In the vertical, so this is an example on the right hand is an example of a fixed model. So we have different levels here, n, n1, n plus 1, n minus 1 and so on. So these are each of these black dots represent the point on which the variables are defined, and as we go below. So in the horizontal, we have a grid which is which grid spacing is given by delta x and delta y, and in the vertical we have delta z. So such grids are created. Now look at the figure on the left hand side, this picture of global. Such grids are described for the entire ocean. And you see these boxes. At every point inside these boxes, we can find the value of these variables like U, V, T, S, and W. The vertical velocity W is calculated from the continuity equation. So this is how a very simple design of the ocean general circulation model is happening. Yeah, so there are different grid schemes based on what kind of stacking that you're using. You have A grid and B grid. In such grids, it is not required that all the velocities have to be at the same point. Sometimes there's a staggering, because sometimes the u velocity is the center and the v velocity at the corner of a given box, and so on. So now, before we go into the solutions, let me give you a brief idea of the ocean, some ideas about the ocean circulation physics. So before the advent of ocean general circulation models, before we had powerful computers which could solve these numerical equations in reasonable time, we had simple models. So these simple models are mathematical solutions to those set of equations. These equations, it is not very easy to find analytical solutions to this full set of equations. They are too complex. But if we are given a system, and we are focusing on some particular features, it is possible to simplify this set of equations and arrive at some solutions. Let me give you an example. These equations, so we have terms like u del u by del x and so on. Now, some mathematicians think that nonlinearity is small. The contribution from nonlinear processes to long-term general circulation is small. So that is one assumption, for example. So if we assume that, then we can drop the nonlinear term. So on the left-hand side, we would have only del u by del t and minus fu. So that's one simplification, for example. Now, there is another simplification possible, that we can assume that the ocean is horizontally homogeneous. Now, this is valid to some extent because, for example, if you take the tropical ocean, in the tropical ocean, that is between, say, we are between 10 degree north to 20 degree north. The sea surface temperature in this region hardly varies between 2 to 3 degrees, right? So if you assume that this variation is negligible, it is possible to assume that the spatial gradients are small. So then all the terms with gradients would disappear. And then there would also be no mixing between in space. So we could drop horizontal mixing, and we could also drop horizontal gradients and so on. So before we had powerful computers, people did solve these equations and found simple solutions to them. So in one such model, the ocean can be divided into 3 simple layers. Okay, so this is like a box, and this box has 3 partitions: one at the top, one at the side, and the remaining. So one at the top is where the winds are directly driving the ocean. That layer is called the Ekman layer. So in that layer, friction is important. Okay, so it is the friction which is dragging the ocean surface and driving the currents and so on. So that is one dynamical regime. So that's called the Ekman layer. Now, when we come close to the continents, close to the coastline, the ocean is continuously rubbing against the land. And this rubbing creates friction. And so very close to the boundaries, the friction becomes important. So that's another second dynamical regime, which is another frictional layer. Now, both Ekman layer and the layer close to the continent are influenced by friction. Yet, they are different in the sense that in one, it is caused by winds, and in another, it is caused by the rubbing with the land boundaries. Now, if we go away from the surface layer and away from the land boundaries, the effect of friction is considerably small. So that layer is called the geostrophic layer. In the geostrophic layer, we basically have a balance between the pressure gradient force and the friction force. So my point is that such simplified models also exist in the science of physical oceanography. Yeah, so a couple of slides back, I described about how the vertical structure of the ocean is varying between different types of models. So there are four examples here. The picture is slightly old. I hope you can see them. It's in black and white, but it conveys the idea that we want to. The first one is a set coordinate model or the fixed box type model. So what we see here is the shaded region is the ocean bottom, and here it is the land. Okay, and eta shows the deviation of the sea surface from its mean height, and that's given mean surface, and that's given by eta. Right. So these horizontal lines divide the ocean into different boxes. So these are the so-called set coordinate boxes, which divides the ocean in the vertical into different boxes. So now what happens here? The number of boxes depend on the depth at any particular location. For example, here you have a seamount. Okay. Seamount is an elevation from the of the ground from the ocean bottom. So at the seamount, the depth is lower. So the number of boxes that is required, number of levels that is required is smaller. You just require one, two, and a little more here. But if the depth is larger, the number of boxes increases. Now let's go to a set coordinate, a sigma coordinate model. That is the bottom left figure, right? So here the number of layers are fixed, and the grid levels follow the bottom topography. So here, these are all horizontal lines with no regard to the structure at the ocean floor. But in a sigma coordinate model, the layers follow the bottom topography. If there is a seamount, the coordinate system, the system of coordinate are elevated. If there is a trench, it goes down and so on. It basically follows the bottom topography. And the other thing is the number of layers do not change depending on the depth. They remain same. Okay. So here, how many layers are there? 1, 2, 3, 4 layers, right? So that is same whether you are near a seamount or you are near a depression. Only thing is that the spacing between these grid points or layers would change. In a sigma set coordinate, sorry, or a fixed coordinate model, the distance between the boxes wouldn't change, whereas here it would change. Now, in the third one, that is a layered or isopycral model. It depends on the density. So, depending on the density structure, the layers would be defined. Now it's time to take some design parameters, and we need to take decisions. How do we design the grid spacing? So what is grid spacing? Grid spacing is, look at this globe again. So you see these boxes, right? So the size of each box is a grid spacing. Why does it matter? The smaller the size of the boxes, you have larger number of grids, and you need to solve for larger number of grid points. So the computational cost becomes larger. Okay, so we need to arrive at a compromise. Now, how do we decide that? The number of grid points are dependent on what are the features that we are looking at. Suppose you have an ocean current, and assume that the ocean current has a width of about 200 meters. Now, when we get the solution, that means a description of u and v, we should be able to see that current in vectors of u and v, right? Okay, so if our grid point is, for example, spaced at 500 meters, there is chance that we might miss it completely. Because if when one grid point is on one side of the current and other grid point is on the other side of the current, we would miss it completely. We don't want to do that. Now, we could go for a very fine resolution. For example, if we have 1 kilometer resolution, we are certain that we would not miss it absolutely. But then imagine from 500 kilometers, we are going to 1 kilometer. So the number of grid points are going to increase exponentially. So the cost is going to go very high. Your solutions wouldn't come in time for you to see the feature. So we don't want that to happen. So we need to arrive at a number that would describe the features correctly. So this is done using a parameter called Rossby radius. Rossby radius is the minimum length scale that is resolved in order to describe the ocean circulation at a given location. So the map on the left-hand side shows you the Rossby radius in kilometers. So if you go to 30 south, the Rossby radius is about 40 kilometers. Now, if you have a feature that is 40 kilometer wide, we need at least four grid points to describe that in a reasonable way. 5 is better, but 4 is reasonable. So we need to have our grid point at 10 kilometers. So in this domain, we need to have a grid point at approximately 10 kilometers. So the Rossby radius is a number which gives you an idea on designing what should be the grid point. Now, when we go to find a resolution, there are, for example, features like eddies. So if we need to resolve them, we need to have even finer resolution. So if you look at this in mid-latitude, the approximate grid size should be about 20 kilometers. Now, the other parameters, what should be the time step? So if you remember a few slides back, I showed you these equations, and this equation would, in a numerical procedure, this term would translate into a time step. What time step should be taken to solve this equation? And because we are converting it into numerical equations, it also has to meet a stability criterion called as a CFL criterion that is given by delta t, that's a time step, should be less than delta x, that's a grid spacing, and c the space speed. And space speed is roughly given by root gh, where capital H is the depth of the ocean. So for large-scale ocean circulation, the sea is approximately 200 meters per second, and therefore the time step that is required is approximately 100 seconds. Now, let me show you some example. So these are results from an ocean general circulation model. Okay.
Sir, can you go back one slide?
You have a question?
Yeah. That deformation of Rossby radius. Can you tell us a little bit about that?
Yeah. Rossby radius of deformation is basically dependent on two parameters. One is the phase speed of the wave that is propagating, and denominator is f, is the Coriolis parameter. So actual calculation would kindly differ, but this is a simple theoretical idea that C by F gives you the Rossby radius of deformation. So it depends on the dominant phase speed, and F is the Coriolis parameter, which is dependent on the latitude where you are. Okay. Right. So the top panel of the slide shows you the sea level, okay, that is measured by satellites. So the scale is given at the bottom, and it runs from, it's in centimeters, run from 1.6 meters. Blue is wherever it is lower compared to a long-term mean, and red is locations where it is higher compared to a long-term mean. So for example, if you look at the Pacific Ocean here, this is where the Kuroshima current is. Here the sea level is the highest, right? And the blue is regions where the sea level is lower. That's all negative in green. Now, the bottom panel is how is the result from an ocean model, which solves for the sea surface, the eta, which I showed you in the previous slide. So we can see a lot of things, like for example, in the subtropical ocean, there is a region where the sea surface height is very high, and which is reasonably well reproduced by the model. This number is something like 60 to 100 centimeters, right? So that's here. It is reproduced by the model. And in fact, all this large scale pattern is reproduced by the model. So you would see some difference in the Indian Ocean, where this data shows mostly red, whereas you also see patches of yellow in the simulation. And this is, I presume, because the way the data is handled. But when we look at the model, we also see that there are differences. Like you see these patches here, which is not seen in the observations. So what I would like to say is that the ocean general circulation models are quite good in terms of reproducing the large-scale features that we can see from data. However, when we come to realistic data at a given point, one has to treat the model result cautiously and see what is it is able to reproduce and so on. So this is the mean picture. Now, what about the variability? So the variability, one measure of variability is given by the standard deviation. So this is the standard deviation of the same data which I showed you before. So you see that there are large standard deviation in regions of large ocean currents like Kuroshio, Gulf Stream, and so on. And there's also a big patch in the Southern Ocean. So all these features are reproduced by the model, but there are differences in the magnitude. So this is an example of the ocean model simulation. So another interesting feature is how the result vary as a function of grid spacing within the model. So the bottom right figure is observation, and the other three resolutions: 0.1, 0.2, and 0.4. So here, this set of simulations show that if we increase the horizontal resolution, that means if we decrease the grid size, the solutions that we get are likely to be better. Okay. So there are good things about the model. There are bad things about the model, and why this happens. So this is still a matter of research, and there are three major reasons for the departure between simulation and observations. One of them is unresolved physics. There are processes which we do not understand yet, and because we don't understand yet, we can't write the equations for them. We can't write an algorithm to calculate them, for example, mixing processes. The second is unresolved length scales in both horizontal and vertical. There are processes which goes unnoticed by the grid size, right? It is smaller than the grid size. And finally, our equations require forcing functions on the right-hand side. The response depends on the quality of the forcing fields. So deficiencies in the forcing fields is a reason for the departure between simulation and observations. So I would like to stop here now, and I'll be happy to answer any questions that you may have.
The last point, can it be the last point, deficiency of forcing fields? What do you mean by that exactly?
Yeah, so if you remember one of the slides, I showed you that the oceans are forced by the winds, heat, and freshwater fluxes at the surface, right? So oceans are forced by the wind, heat, and freshwater flux at the surface. Now you have a grid here, right? And you need the data for the winds at each of these grid points. And where would that come from? Ideally, that should come from observations. But we can't get observations at every 1 kilometer. So what we do now is we rely on so-called reanalysis products. Reanalysis products from the atmospheric models. So these atmospheric models, atmospheric reanalysis systems, use a model, atmospheric model, use available observation, synthesize them, generate a product, and release those products. So if you want to do an ocean forecasting, we need to take those products and force the model. And because we are using a force, because you're using a model product, that model product has deficiencies. That's one example.
So that will propagate here.
That will cause an error in the simulation. So the second possibility is to use some satellite data, and satellite data also has errors, so they are not perfect. So the errors in forcing fields like winds, heat fluxes, and freshwater fluxes would affect the simulation that we would get.
Thank you.
Okay. Any other question? Okay, let me see.
Sir, can you repeat the Rossby radius?
Rossby radius gives you Rossby radius is a number which gives you an idea of the length scale that is to be resolved as a function of latitude and stratification. Okay, so given a location, what is the scale? What is the length scale that is to be resolved in order to obtain a reasonable idea of the ocean features? So that depends on the stratification and the latitude. That's why we have C by F. Okay, and this is a calculation based on actual data on what the C by F should be. So as we approach the tropical region, this is about 140 meters. So you can manage with the larger grid. But once we go to the subtropical region, 30 degrees, it's about 40 kilometers. So the length scale is small, that is to be resolved is small. So here we have to resolve 40 kilometers, whereas here we have to resolve 80 kilometers, right? So it is doubled. So we need to have 4 grids within 80 kilometers, whereas here we have to have 4 grids within 40 kilometers. Okay. Now, if we use an ocean model with a uniform, we have to do justifies for the entire domain. So in this model, ideally, we should have we should be able to resolve 40 kilometers.
Okay, sir.
Is that better?
Yeah.
Okay. Okay, so if there are no other questions, we would break now and assemble back at 11 o'clock. All right?
It is 11 o'clock?
11:15.
Okay, sir.
Vinay, there are some questions in the chat box.